Hello, so this is the first Zoom meeting on the chapter 10 review. And so we will start the chapter 10 review and go up to question 4. So let's go over question 1. Use the figure below to answer those. So what kind of energy does the ball A possess initially when at rest at the top of the hill? What kinds of energies are involved as ball A moves down the hill? What kind of energy does ball A possess when it reaches the bottom of the hill and stops moving after hitting ball B? And where did the energy gained by ball B, where did the energy gained, allowing it to move up the hill, came from? So you see how the man is holding the ball A in place and then releases it. And then in the end, it's ball A that is at the bottom of the hill where was ball E, and ball E has moved up into a smaller hill. And so at first, initially, when ball A is held in place here, it's possessing potential energy. The difference between potential energy and kinetic energy is that potential energy is due to position or composition of chemical bonds. But here it's really due to position. It's the fact that it's higher up, so it will possess energy due to that elevation. And it has no kinetic energy at that point because there is no speed, no movement. Kinetic energy is due to energy of motion. Now, when you are releasing ball A and it moves down the hill, it will accumulate kinetic energy. So the potential energy will change into kinetic energy. And that's due to the speed, of the ball going down. But it also loses some energy to frictional heating. Frictional heating is the fact that on the path where it goes, it causes some friction, and that's heating the surface there. And so there is some energy lost in that frictional heating. But when ball A reaches the bottom of the hill, it has more kinetic energy than potential energy now. And when it hits ball B, the kinetic energy will transfer from ball A to ball E. And ball A, by doing this, by transferring its energy to ball B, we say that it's work. Ball A is doing work on ball B. And that allows B, because then B has energy, and it allows it to move up the smaller hill, right? It moves up to that smaller hill. And so at the end, ball B will have more potential energy than initially, because it's higher up into that intermediate hill. So ball B will accumulate potential energy. And ball A at the end only has potential energy that is due to that lower position, right? None of them has kinetic energy in the final state. They have used that energy for ball B to move up and for ball A to do work on ball B. And so they both have just the potential energy due to their new position now. So question 2 now. A friend of yours reads that the process of water freezing is exothermic. This friend tells you that this can't be true because exothermic implies hot and ice is cold. So is the process of water freezing exothermic or not? And if so, explain this process so your friend can understand it. If not, explain why not. So yes, the freezing of water is an exothermic process, that's true. And exothermic means that water is releasing heat to the surrounding when it freezes. So there is indeed a release of heat from water when it goes from a liquid to a solid. You have to think of the intermolecular attractive forces that are in play between the molecules of water to understand this. I have done a little drawing and let me show you that. So here I'm showing you how the molecules of water in the solid, so in the center drawing here, molecules of water when in the solid, they are packed but orderly. Notice how they all have the same orientation. And so there is a lot more, even though my drawing doesn't really show that, but there is a lot more intermolecular attractive forces between the molecules. And those red dots here are the intermolecular attractive forces. So yes, those dots represent the intermolecular attractive forces. And in the case of water, there is London dispersion forces, like in any molecules, dipole-dipole interactions, because the OH bonds are polar, and then hydrogen bonds, because hydrogen is bonded to oxygen. And because molecules are very neatly packed, the strength of those forces is stronger in the solid. There is more of the forces holding the molecules in the solid phase than in the liquid phase. If you notice here in the drawing on the left, for the liquid phase, the molecules of water are oriented randomly, so there is no order anymore. And so notice how the intermolecular attractive forces, are longer. There is more, more dots, if you will, between them, which means the distance is not as close, and it's making the forces of attractions a little more weak, even though it's still very strong in the water liquid. So there is less strength in the forces of attraction between the molecules of water in the liquid phase. And so that's why they can still move around and be, randomly oriented, and they can rotate, if you will. So there's still some movement allowed in the liquid phase. So here, to summarize question 2, the liquid water is held less strongly by intermolecular attractive forces than solid ice. And the reason why it's held less strongly, it's because it's, still a liquid phase, not solid phase. And so this allows water molecules to move more freely around each other in the liquid phase. So there is more freedom of movement in the liquid phase, which is not the case in the solid. In the solid, there is less motions, right? It's just vibrating around a fixed position. But in the liquid phase, you can roll around, flow. So the liquid water has more kinetic energy, or energy of motion, than the solid ice. And so the difference in energy between the liquid and the solid phase will have to be, released to the outside when the liquid becomes solid. So when liquid water becomes solid, the excess energy between the liquid and the solid is released to the surrounding, right? And so that's why it is exothermic. You have a release of energy to the surrounding. Water loses energy to the surroundings and becomes more stable. This time the intermolecular attractive forces are holding the molecules into place. They are just vibrating. So question 3, what does it mean when the heat for a process is reported with a negative sign? Is the system gaining energy or losing energy? And is the process exothermic or endothermic? So this is something you really need to learn. This is important to make the distinction. When your system has a negative energy change, if it goes through a process, and if it's negative, that means it's losing that energy to the surroundings. It's like you're removing that energy from the system. And so it goes to the surrounding, and so then it is exothermic for the system, right? Because the system is losing the energy to the surrounding. It is also, you notice here how it is important to really define your system well, because then otherwise you get things inversed. So when a system has a negative energy change, it means it's losing that energy to the surrounding. So it is exothermic for the system. And when the system has a positive energy change, that means it is gaining that energy from the surroundings. And so it will be an endothermic process for the system, right? Because it gains that energy from the surroundings. So this seems like detail, but it is important to remember that, especially in sapling, at some point there will be a question where you will be expected to remember that you need a negative sign for your energy change value when it's an exothermic system, exothermic process. So, and then question 4. You place a hot piece of metal into a beaker of cold water. Eventually, what is true about the temperature of the metal compared to that of the water? So imagine you have this cold beaker of water, and you can imagine just a regular glass of cold water. And you have this hot piece of metal, and you drop it in it. And drop it gently, because otherwise you can break your beaker. And you can imagine that the metal will cool down, right? You imagine that the metal, because it's now in the cold water, it will cool down. The temperature of the metal will go down. And then for the water, it will be the reverse. The cold water will warm up thanks to the piece of metal. And so the temperature of the water will go up. And eventually, the temperatures of the metal and of the water will be the same. You will reach what we call an equilibrium, where the temperature of both the metal and the water will be the same. But for the metal, it will be a cooling down, and for the water, it will be a warming up. So then, label this process. So let me show that more. Label this process as exothermic or endothermic if we consider the system to be the metal. So remember how when you are deciding if it's exothermic or endothermic, it is very important that you define your system well before you decide, if it's exothermic or endothermic. So if you place yourself in the metal, if your system is the metal, then is it an endothermic process or an exothermic process? So remember, the metal is cooling down. It's losing energy, right? Because its temperature goes down. So the metal is releasing energy to the surrounding, and the surrounding in this case is the water. So if the metal is surrounding energy to the surrounding, yes, what did I say? Releasing energy to the surrounding, then that means it's endothermic for the metal, right? Because it's exothermic. Sorry, I get confused here. For the metal, it will be exothermic. Exothermic because it releases heat to the water, right? So, but then now if you're placing yourself in the place of the water, then it's going to be the reverse, right? Now the water is warming up. So water is absorbing energy from the metal. The metal in this case is the surrounding. And so water is absorbing energy from the surrounding. So we say it's endothermic process. I'm sorry for getting those mixed up, but it's written properly here. The water absorbs thermal energy from the metal. It absorbs it, so it is endothermic for the water. So notice how, between water and the metal, if it is an exothermic process for one, then it is an endothermic process for the other automatically.